We've got the worked solutions here for the P3 paper from 2018, and this is the March series. So it's paper 32 from March 2018. Question 1 is about using the trapezium rule that is on your formula sheet. And that looks like this. So h is equal to pi by 4, which is the length of our integral that we get from here, and we're going to divide that into 3 intervals, so h will be equal to pi by 12. Then we need to work out the y values for each of the x values. So our x values for the edges of the intervals are as shown there, and we'll work out the y value by substituting them into the square root of 1 minus tan x. And these are the values we get for the y ordinates. Make sure you give enough decimal places. Our answer has to be to 3 decimal places, so you should show each step to at least 4, so that when you make your final answer at the end, you know for sure you haven't lost any accuracy. And we get a final answer of 0.525. So if we rewrite this as 1 minus 4x to the power of a quarter, we can easily apply the formula that is on your formula sheet for doing binomial expansion. We want to do it as far as the x cubed term. And this is what we get if we use that formula. Just remember that the whole of that minus 4x portion here must be put into these brackets here when you pop it into the formula. Don't forget the minus. And that then simplifies down to 1 minus x minus 3 over 2x squared minus 7 over 2x cubed. For question 3, we need to expand 3x plus x and 3x minus x, the cos of those. So just from the formula sheet, I've written down those 2 expansions already. Now, the top one, of course, 3x plus x is 4x, so this is equal to cos of 4x, and the bottom one is equal to cos of 2x. So we can substitute those into our formula that the equation, the expression that we've got up at the top of 4x plus cos of 2x, and replace them with these instead. And that's looking like this. Now you can see that we've got a minus sine 3x sine x and a plus sine 3x sine x, so they cancel out, and we will be left with it being half of, and then we've got the cos 3x cos x happens twice, which of course leaves us with the half and the 2 cancelling, so we get cos 3x cos x as was required. So the first thing we're going to do is use the identity from the previous part of the question and swap it out for that cos 3x cos x, which then gives something that's much easier to integrate. So we'll go ahead with the integration now. Now cos integrates to sine, and using the reverse chain rule on it, we get a quarter sine 4x, and then a half sine 2x, between limits of pi by 6 and minus pi by 6. So now if we substitute in those limits, we'll have a quarter sine of pi by 6 times by 4, so that'll be 2 pi by 3, plus half of sine, oops, forgot the bracket there, so sine of 2x, so that'll be pi by 3. Take away quarter sine of negative 4 pi by 6, which would simplify down to 2 pi by 3, and half sine of negative pi by 3. Now we're looking for exact values, so do not reach for your calculator at this point. You need to be working on exact values, because just look at our answer that we're trying to get to is 3/8 root 3. So make sure you're using the exact values of sine 2 pi by 3 and so on. So I've substituted in the exact values for sine 2 pi by 3. You can see my little scribbles at the top right hand side of working things out. You should know this identity triangle here, and also your sine graphs and cos graphs, so you can work out those exact values easily. All right, now if we go through simplifying them, oh, and also one more thing, this is a show that question. We're already given the answer, so do not skip any steps. You must show your substitution in and your full working all the way through to get the marks. So now we'll simplify that down. And then we get that that comes to 3/8 root 3. So for the start of question 4, we want to show that that equation can be expressed as a linear equation when we take log y against log x, or rather the natural log, ln y against ln x. So we're going to work through rearranging that equation and then show that it will come to a linear one. So first ln of both sides, and then we're going to use the properties of logs to sort this out. We end up with this, so we can explain that this part here is a constant, and so is that bit there. So it's not a variable. Therefore, we've now got a linear equation. We've got an equation that's in the form of y equals mx plus c. So this makes a linear equation. We'll form a straight line, and the gradient is 3 over n, because that's the portion being multiplied by ln x, and the y-intercept will be 1 over n ln a. Now we're going to work out what n and a are, so I've just written down the information that we had from the previous slide. I'm using the form of the equation where we haven't divided 3 by n, just because it's going to be easier to work with. So we'll substitute in those values and work out what n and a have to be. So we get these two equations when we substitute in those values. So now if we work out the values of those logs, we get these two equations, so we're going to solve them simultaneously. I'm going to do a subtraction of these equations so we can eliminate the ln a, and then we can work out n. Like this, and then we get that n equals 1.6998, which rounds to 1.70 to 2 decimal places, which we were asked for in the question. Now we've got n, we can work out a. And if we work that through, we get that a is equal to 2.90. Okay, so for parametric equations, we need to find dy by dt and dx by dt and use them to work out dy by dx. Again, this is a show that question, so do not skip any steps at all. You need to show all of your working. So if we differentiate y, then we get 4 sine 2t, and if we differentiate x with respect to t, we will have 2 plus 2 cos 2t. Now dy by dx is equal to dy by dt multiplied by dt by dx. So we get 4 sine 2t over 2 plus 2 cos 2t. And we need to turn that into something to do with tan of just regular t rather than 2t. So we're going to use the double angle formulae to try and sort this out. So using the double angle formulae gets us as far as this. Now when you're doing the cos 2t, you want to look for something that's going to help out, because there's 3 options for cos 2t of what we could turn that into. But we want tan, so we want to end up with sine on the bottom and sine on the top and cos on the bottom. So I've gone for the version of cos 2t that leaves us just with cos on the bottom. So now if we work through that, we'll get 8 sine t cos t over 2 plus 4 cos squared t minus 2. So that those 2's cancel on the bottom, and we can simplify the 8 over the 4 to be 4 sine t cos t over cos squared t. So one of the cos on the top will cancel with one of the cos on the bottom, and I've just realized it's not 4. 8 divided by 4 is 2. So 2 sine t cos t over cos squared t, that cancels down to 2 sine t over cos t, which equals 2 tan t, as was required. I've just copied across the information we need from the previous slide to do part 2. We're going to find when the gradient is equal to 2. So set that equal to 2 and solve the equation. And I have just spotted, I did not read the question properly, the gradient of the normal is 2. So the gradient of the curve at that point will be minus half the negative reciprocal. I'm sure lots of people probably made that mistake in the exam. So tan t is equal to negative 1/4. And if we just take a look at the picture of tan, it goes like this with an asymptote at pi by 2 and negative pi by 2. We want to know when that's equal to a negative 1/4. So we can just do the inverse tan of minus 1/4. We're only going to have one solution in the range that we're looking at. So that gives us t, and now we need to substitute that in to find the value of x using the equation of what x was in terms of t from the first part of the question, which comes to 0.961. So question 6 is a differential equation, first giving us a show that question that should be fairly straightforward as it's only worth 1 mark. So make sure you don't miss any steps of working, that you show everything that you're doing. So if we set y equal to tan squared theta, because we're just being asked to differentiate that tan squared theta, we need to show how that works. So we're doing the chain rule, so it'll be 2 tan theta multiplied by the derivative of tan, which is sec squared theta. Now sec is 1 over cos, so that becomes 2 tan theta over cos squared theta. Now we're going to solve that differential equation. I've just copied it across on the right there so we can work with it. So for this one, we're going to need to separate the variables. We want x on one side and theta on the other. So once we've separated them, we're going to integrate both sides. But before I do, I'm going to separate that fraction on the right-hand side into two things we can integrate more easily. Since part I took us through how to integrate tan theta cos squared theta, we can recognise that it's just going to integrate back to tan theta. So x integrates to x squared over 2, and 2 tan theta over cos squared, we know from the part 1 of this question, that will integrate to tan squared theta. 1 over cos squared is sec squared theta. If you look on your formula sheet, you'll know that if you integrate sec squared theta, you get tan theta. And then, of course, plus c. So now we'll substitute in when theta is equal to pi by 3, so we can work out the value of x that we want. So x squared will become, now I've just realised I skipped a step, we need to go back and work out c first. So when x is 1, theta is pi by 4, we're going to use that to work out c. Now tan of pi by 4 is 1, that makes things quite simple for us. So c is minus 3. Now we can carry on and work out when, I'll just switch the colour, when theta is pi by 3, what x will be. And if you work that through, you'll get a final answer of x equals 2.54, and we're going 3 significant figures, so we leave it at that. Part 1 is about knowing your graphs, so just a little reminder of what e to the x looks like. It's one that goes like this, so that would be y equals e to the x. From there we can work out y equals e to the 2x would be similar, it would just go a little steeper. Now e to the minus x would cause a reflection in the y-axis, and then adding the 6 will shift it up by 6, so it will go something like this. So this is y equals e to the 2x. This is y equals 6 plus e to the minus x. And then you need a statement to accompany it. So since there's only one point of intersection, there will be only one real root to that equation. For part 2, we want to show that there's a root between 0.5 and 1. So if we rearrange this to be e to the 2x minus 6 minus e to the minus x, then we're looking for a solution around that being equal to 0. So if we put in 1 and 0.5 and show that there's a change in sign, then we'll show there's a solution between them. So for part 3, we want to show that the equation that we've got here for the iterative formula will be equivalent to the equation that we started with on the previous slide, so that the solution to one will also be the solution to the other. So if we start with the formula that we've got for the iteration, multiply by 3 by the 3, and then if we take e of both sides, then we'll end up with this. Now at this point here, divide through by e to the x, and you'll see we've got the same equation. And then finish off with a statement to say that because they are equivalent, as we've shown, then the solution to one will also be a solution to the other. Now we're going to go on and use that iterative formula to find the root. We want the root to 3 decimal places, and we need to give the answer for each iteration to 5 decimal places. Now we already know there's a root somewhere between 0.5 and 1, so that would be a good place to start. So we had to go quite far to be sure with this one. Now we've got to a point where we know that to 3 decimal places, x will round to 0.928 to 3 decimal places. I'm going to start question 8 with separating into partial fractions. The first thing we're going to do is check the form of the equation we're starting with. So just take a little look at that equation to see what we need to separate it into. Now the order of the top is less than the order of the bottom, so we won't have a whole number on its own at the front, but we have got a quadratic at the bottom, and we need to take care to arrange that properly. So we get it in this form here because of that quadratic of x squared plus 9, we need the bx plus c on the top there. So now we'll go through equating coefficients or substituting in values to work out the a, b and c. So we get this equation from the top lines of the fractions, and first I am going to substitute in x equals minus a half because it will equate this bracket here to 0, and then that'll help us to get the value of a. So we get a equals 3. Next I'll compare the constant terms, so we have 27 on the left hand side, we've got 9a on the right and c on the left. Well, since a is 3, 9 times 3 makes 27, so c must be 0. Now if we compare the x squared terms, then on the left we've got 5, on the right we've got a and 2b. Now since a is 3, b must be 1. So we have this for f of x. So for part 2, this integral of f of x becomes the integral of the partial fractions we just worked out in part 1. We're going to work that through now. I've just realised a mistake on the previous slide, that the 1 was the coefficient of x in that partial fraction. So we actually need this top of the fraction here. It's not 1, it's x, which makes the integration much easier to do. So if we integrate 3 over 2x plus 1, we get 3 over 2 ln 2x plus 1. Integral of x over x squared plus 1. The top is a multiple of the derivative of the bottom, and it's half of the derivative of the bottom, since if we differentiate x squared plus 9 we get 2x, whereas we've only got 1x on the top at the moment. So we get a half ln x squared plus 9 from that second one, and we're going to do that between 0 and 4. Substituting in those values looks like this. Now we're going to use our law of logs and leave our answer in terms of ln. So ln 9, so 3 over 2 ln 9 becomes ln 9 to the 3 over 2. 9 to the power of 3 over 2 is 27. The half then goes to the half ln 25 becomes ln 25 to the power of a half. 25 to the power of a half is 5 minus. So ln 1 to the power of 3 over 2, well, 1 to the power of anything is still just 1, so that's ln 1, and then ln 9 to the power of a half, so that's ln 3. So ln 27 plus ln 25 is the same as ln of 27 times 5. So that's ln of 135 minus ln of 1 times 3. And then if we subtract logs, we can divide what's in them. So ln of 135 divided by 3 is 45. Question 9, we're told that u is a root of the equation, so we can substitute u into that equation, work out the missing part to work out what k is. Now on the right hand side, I've just worked through what 1 plus 2i squared is and what 1 plus 2i cubed is, so we can substitute those into this equation. We can work that through to find that k is 15. So now we need to find the other two roots, and I've just copied across on the right hand side what we had on the previous slide. So we know that if 1 plus 2i is a root, then its conjugate will also be a root. So we can write that one down straight away. So 1 minus 2i is another root. Now, using the factor theorem, we know that if we've got a root, then if we do x minus that root, then we will have a factor of the equation. So we know that if we expand this, it will be a factor of the original equation. We can use that to find the other root. And this comes to x squared minus 2x plus 5. From here we know that if we do x squared minus 2x plus 5 multiplied by a linear factor, so ax plus b is representing our other factor that we don't know yet, then that will have to multiply out to 2x cubed minus x squared plus 4x plus 15. So if we take a look at the coefficients of some of those terms, so x cubed, we need it to be a on the left hand side has got to equal 2 on the right hand side, so a must be 2. Then if we compare the constants on the left hand side, we will have 5b has got to be equal to 15, so b must be 3. Therefore 2x plus 3 is another factor. So our final root is that x equals minus 3 over 2. Okay, now we need to do some work with an Argand diagram, and the first thing is to know that the modulus of z minus u is equal to 1. Now what that is telling us is that the distance from u to all the points z have got to be equal to 1. So have a think of what that looks like. It's going to be a circle around u with a radius of 1. So it looks like this. Now if your drawing is not that great, you might want to put a label on it to say exactly what you intend it to be. So this is a circle, radius 1, center u. Now my diagram is going to get a bit full, so I'm taking that off for now. Now determine the least value of the argument of z for points on this locus. So z can be anywhere on that circle. We want the point on the circle which would give us the smallest argument of z, which is the angle between the line 2z and the x-axis. So that's going to be just here, where we can make that line be a tangent to the circle. So this is where z's got to be to make that argument of z the least. So this here is the argument of z. And then we need to work out how big that is. So we've got this line here, which is a radius of 1, and the radius and the tangent always form a right angle. So from there we can make ourselves a right angled triangle. And we can use the modulus of 1 plus 2i for the length of the hypotenuse of that triangle, so that's going to be root 5. From here we can work out this angle here. I'm just going to switch up colours to keep track of what we're doing. So if we call that angle theta, then sine of theta will be the opposite over the hypotenuse, so 1 over root 5. So therefore theta is 0.4636. Next we want to work out the argument of u, which will be this angle just here, right down at the base of what we're looking at. So the angle between the line out to u and the x-axis. So think about that as being a right angled triangle. We've got the bottom is 1, the height up there is 2, so we can use that to find the argument of u. So the argument of u will be inverse tan of the opposite of the adjacent, which is 2 over 1, or inverse tan of 2. So the argument of u is 1.1071. From there we can do a subtraction to find the argument of z. So the argument of z will be the argument of u minus the theta that we worked out above. So the argument of z, corrected 2 decimal places, is 0.64. And finally we come to our vectors question. We want to find the position vector of the point of intersection of the line and plane that we've been given. So at the point of intersection, we need to satisfy both of these equations. So if we substitute in the values from the line into the equation, we can work out what mu will need to be. So this is what we get when we take the top line being x, the middle line is y, the bottom line is z from this equation, and then substitute that into the equation for the plane P. So if we work that through, we get mu equals -2, and then substitute that into the equation for the line. If mu equals -2, then we can get all of the other values for the ijk components. So 2 minus 1, 3 is the point of intersection of that line and plane. Now we want to find the acute angle between the line and the plane. So we're looking for this angle just here. And what we'll use is the angle between the normal to the plane and the line to be able to work that out. So the vector for the normal I'm just going to call n, and that's 2 minus 3 minus 1 taken from the equation of the plane. The vector we need to use for the line is the direction vector of the line, which is this portion of the line equation. I'm just going to call that d for us to be able to refer to it easily. So that'll be a 1, 2, minus 2 that gives us the direction vector of the line. And we can use the scalar product to be able to work out the angle between them. So the scalar product is -2. And then the modulus of n is root 14, the modulus of d is root 9, which of course is 3. So cos theta is -2 over 3 root 14, so theta then becomes 100.26 degrees. So what we've actually ended up with here is, if we go back to our original drawing, we carry on that normal line down there. We've ended up with this angle here, because it's more than the 90 degrees, so it's 100.26. Now if we subtract the 90-degree portion of it from the normal to the plane, we'll be left with the angle between the line and the plane itself, which is 10.3 degrees. Okay, so we'll break down what we're being told about this second plane Q. So Q is parallel to L. That means that the direction vector for L can be found on Q. since the line and the plane will never meet. So the direction vector of 1, 2, minus 2 must be on that plane. Then the next thing is that it's perpendicular to P, which means that the normal to P is also on that plane. So it forms another vector that is also on Q. So that's 2 minus 3 minus 1 is a vector on Q. And the last piece of the puzzle that we'll need is that 0, 4, minus 1, so that position vector is a point on the plane. So if we do the vector product of the two vectors that we know on the plane, we will get the normal to the plane. So the vector product of those two vectors will give us the normal, and then we can use the position vector to substitute in and work out the last part of that equation. So minus 8 minus 3 minus 7 is normal to the plane. We can take out the factor of minus 1 from that and also get that 8, 3, 7 is normal to the plane if we're just going the other direction. So the equation of the plane will be 8x plus 3y plus 7z equals some constant d. Now if we substitute in our position vector, we can work out what d is. So substituting those in gives us that d is 5, and we can write our final equation.